General equilibrium, competitive equilibrium, or Walrasian equilibrium. All these three terms mean the same thing. In the previous video, I explained what we mean by Walrasian equilibrium and how we describe it and how we calculate it. In this episode, I would like to show you a numerical example. I'm going to first solve an example where there's no production, but in the next video, I'm going to solve another example with production. Okay, here's the question. Consider an economy with two goods, X and Y, and two consumers, consumer A and consumer B, Ali and Bob. Let Px and Py be the prices for these goods. Ali's utility function is given by this functional form, and his initial endowment is 0 for good X and 4 for good Y. Bob's utility function, on the other hand, has a different functional form as given, and his initial endowment is 2 for good X and 0 for good Y. Well, the question is, what is the Walrasian equilibrium X and Y and prices Px and Py? All right, remember the Walrasian equilibrium has two parts. The first part, the consumers should maximize their utility functions subject to their budget constraints. And then the market should, so the second condition of the Walrasian equilibrium is that the market should clear, meaning the market supply must be equal to market demand. All right, so we first need to find the market demand. And for this, we need to find the demand of these two agents, A and B. So how do we do that? Well, that means they're going to maximize their utility function, means maximize utility subject to the budget constraint. Well, maximizing utility by choosing XY, obviously. I'm not putting A or B here. By the way, this is how I summarize the question. These are two agents' utility function and their endowments. I'm not going to put AB here because I'm going to give a generic utility maximization problem and budget constraint. So what is the budget constraint? Let's clear about this. Well, the budget constraint, as always, expenditure equals income. So here, these guys do not have an income like money. All right. So these guys have only endowments. There's money, but nobody endows or sort of owns money. What they can do, they can use money to make exchange. How do they do that? They can sell their products. They can sell their, initial endowments, and with the money they generate, they can buy consumption good X or consumption good Y, or both. All right. So therefore, their income is basically the amount of money they can generate by selling the entire endowment they have. Obviously, they don't have to spend all their endowments, so they can consume some part of it and sell the rest. That's totally up to them. But nevertheless, the income that these agents are going to have is going to be Px times Wx and then Py times Wy. Remember, Px is the price of good X, Py is the price of good Y. And so this is the income that they can generate. Well, then what is the expenditure? Well, it's X Px plus Y Py. So when I solve the maximization problem for agent A, I'm just going to put superscript A everywhere. I mean, on top of X and Y and U. And when I solve the utility maximization problem for B, you can just put B everywhere. Okay? So how do I solve this? Well, because the utility functions are having convex indifference curves, the solution, the optimal solution will be on the interior, so there's no boundary solution. Basically, instead of writing down the Lagrangian and etc., you just use marginal rate of substitution equals price ratio minus price ratio equality, and by using this, get some relationship between X and Y for each agent, plug that back to their budget constraint, and solve for X and Y. All right, so what does that mean? Well, I'm going to do this first for agent A and then B. Well, agent A's marginal rate of substitution, oh, by the way, maybe it's time to put A here and B here, because This is consumption of good X for agent A, and this is consumption of good X for agent B, and agent A and B may consume different amounts of good X. So these terms are going to be different. So for that reason, although they denote X denotes good X, consumption of agent A, let's denote it X superscript A. Okay? All right, so what is the marginal rate of substitution of agent A? Well, minus marginal utility with respect to good X, which is YA, and then the marginal utility with respect to good Y, XA, equals minus PX over PY. So just do the, cancel out the minus terms, do the cross product, you're going to get XA PX equals YA PY. All right, well, that's it. Plug this to individual A's budget constraint. It is going to give us XAPX. Oops, I don't know why X is now superscript. Sorry. PX plus YAPA. Well, YAPA is exactly equal to XAPX. So I have 2 XAPX, all right, equals to WX is 0. So this term is going to be 0, and WY is 4, so it's going to be 4 times PY. All right. Well, if you divide both sides by 2PX, so I leave XA alone, it basically means 2PY divided by PX. So that's it. This is the optimal consumption for good X for agent A. Well, use this optimal condition between X and Y. You're going to plug XA here. That means I'm going to multiply this term with PX, so the PX's will cancel out. I'm going to divide both sides by PY just to leave YA alone. So what do I get? YA is equal to 2. It doesn't depend on PY, PX. That's perfectly normal because this PX term vanished because the WX was 0. All right, and so we don't have PX or PY term here. So there's no mathematical error or algebraic error here. Well, that's it. This is the demand for agent A. But to find the market demand, I also need to find the demand, optimal demand for agent B. Well, marginal rate of substitution for agent B is again equal to price ratio. Remember, this is the assumption for general equilibrium or Walrasian equilibrium. Everybody is a price taker. They take the price as given, so the prices do not change for agents. All right, well, that means if you take find the marginal rate of substitution of this guy, its derivative with respect to X is 1 over XB and divided by 1 over YB equals minus PX over PY. So remember, this is YA divided by XB. So if you do the cross product, this is what you're going to get. XBPX equals YBPY, which is very similar to what we got for agent A, which is perfectly normal because this utility function is a concave transformation of this one. Meaning if you just take the natural log of this function, you're going to get exactly this. So in that sense, these preferences are equivalent, meaning the marginal, they represent exactly the same preference relation. That means the marginal conditions of these two utility functions must be the same. All right, and voila, for that reason we have this similarity. Well, what am I going to do next? I'm going to plug this to agent B's budget constraint. So it is XPX or XBPX plus YBPY, but again YBPY is equal to XBPX, so I'm going to have 2 XBPX equals to, the WX is for agent B is 2, so it's 2PX plus WY is 0, so PY term will vanish. Divide PX's from both sides and 2's from both sides. Well, then that means the optimal consumption for agent B on good X is going to be 1 unit. And in order to find the optimal Y, well, use this equality. So XB is 1 here, so therefore YB is going to be PX over PY. Okay, that's it. So I basically found the market demand. Let's summarize it. Market demand for good X. So what is it? Well, it is XA plus XB because there are two agents. And what is it? XA is equal to this term, 2py over px plus 1. All right, XB is equal to 1. And then for good Y, the market demand is YA plus YB, which is equal to 2 plus this term, 2 plus px divided by py. All right? So that was the first part of, or first condition of Walrasian equilibrium. All consumers should maximize their utilities subject to their budget constraint. The second part of the Walrasian equilibrium is the requirement that the market must clear. I mean, market supply must be equal to market demand. So what is the market demand? We just got them. What is for each good? What is the market supply? Well, here there's no production, all right? There's no product X and Y coming outside. It's only the initial inputs these guys bring to the market. So the supply, the market supply for good X is WXA plus WXB, which is agent A brings no good X, agent B brings 2 good X, so the total supply is going to be 2. Good Y is basically WYA plus WYB. So the Y's are 4 and plus 0, and so the total 4 units of good X. Okay, so that's it. The market demand must be equal to market supply, therefore means for good X, the demand is equal to 1 plus 2py over px, which must be equal to supply for good X, which is 2. So send this 1 to the other side. I'm going to have 1, right? So basically, py divided by px must be equal to 1 over 2. Can I calculate px value or specific px or py value? No, it's just a ratio. Py over px must be 1/2. All right, let's see what I can get when I clear for good Y, clear the market for good Y. The demand for good Y is 2 plus px over py, which must be equal to the supply for good Y, which is 4. So send this 2 to the other side. I'm going to have 2 here. And so, you know what? Px over py is equal to 2. Well, if you look at carefully, you're going to see actually this guy is just the flipped version of this, right? Py over px 1/2 means px over py is 2. So meaning they're identical. So whether you clear the market for good X or good Y doesn't matter. You should get exactly the same ratio. You may wonder, but we couldn't find any px, specific px value or specific py value, which is fine. And in fact, this is what we get in Walrasian equilibrium. It basically says the following. In this market, there are infinitely many prices that that may form an equilibrium, meaning that will clear the market. So infinitely many prices. But all of those prices must satisfy one property, which is whenever we calculate their ratio, px over py, it must be equal to 2. Which means the price for good X is equal to $2, all right? And then the price of good Y equals $1. So this is one set of equilibrium prices. However, if the price of good X is $10, but the price of good Y is $5, then this is again an equilibrium. I mean, it will clear the market. So I summarized all our findings. I just want to conclude what the Walrasian equilibrium will look like. So remember, these are the optimal demands for consumer A and B, and this was the Walrasian equilibrium price ratio. So all you have to do is just to plug them back to here. Well, so therefore, a Walrasian equilibrium should look something like this. This is the demand for good X and Y for agent A. This is demands for good X and Y for agent B, and then the price ratio. Okay, so this is how we summarize a Walrasian equilibrium. So this is a consumption, a bundle, all right, and then, or the commodity bundle, and then this is the price ratio. The Walrasian equilibrium will always look something like this when we have two goods and two agents. Well, if you plug this number here, what we're going to get is XA, well, PY over PX is 1/2, so therefore it's 1. But he's going to consume 2 units of good 2, and then agent B, he's going to consume 1 good 1, and then PX over PY 2 units of good 2, and then remember the PX over PY ratio is going to be 2. All right. So at the end, that means if this is the initial endowments they bring to this market, agent A, is going to sell 2 of his good Y to the other agent, and the other agent will buy it, and in return he's going to sell 1 of his good X to the other agent, and because good Y was more abundant than good X, in fact it was 2 times more, that kind of explains why the price ratio is going to be 2. I mean, the price of good X is going to be 2 times more than price of Y. And then that makes sense because, as I said, X is the amount of X in this market, the supply of X in this market is half of the supply of Y. And so the final price is 2 times more. Well, here, obviously, the ratio 2 here and the ratio 2 here is very much correlated, obviously, because of the utility functions. So these are very nice utility functions. So this ratio here perfectly translated to this ratio. In general, though, we may not have it because the utility functions may be different. Here, both agents having the same utility function also plays an important role. And so, yes, this is exactly how we find the Walrasian equilibrium for a problem where there's no production. So in the next video, I'm going to give you another example, in fact, the same example with production, okay?